What if the Big Bang was not the beginning of matter, not the beginning of energy, not the beginning of time itself? What if the moment we call the origin of everything was actually a transition, a boundary, a point where one phase of something much larger collapsed into something new, and what we observe when we look back 13.8 billion years is not the start of the story, but the start of our chapter in it? This is not a philosophical question. It is not mythology dressed in technical language. It is a live scientific problem with peer-reviewed papers, competing mathematical frameworks, and credentialed researchers at major institutions actively arguing about it right now. Loop quantum gravity produces a universe that existed before ours. Conformal Cyclic Cosmology, developed by a Nobel Prize winner, describes an entire previous cosmos whose infinite future became our Big Bang. Eternal inflation places our Big Bang as a single local event inside a structure that has no beginning in any model currently on the table. These are not fringe proposals. These are published frameworks with formal mathematics behind them, and the central question they are all trying to answer is the same one. What was here before? Here is the core tension this entire story lives inside. Our instruments can only see back to 380,000 years after the Big Bang. Before that point, the universe was too hot and too dense for light to travel freely. Photons were trapped, scattered, absorbed before they could move anywhere. The universe was opaque. What we call the cosmic microwave background is the afterglow of the moment that opacity lifted, the oldest light we can directly detect, and it sits like a wall at 380,000 years. Everything before that wall is inference. Everything before that wall is math. Now here is the thing nobody says out loud when they explain this. Inference is not ignorance. Math does not stop at an observational wall. The physics of what happened in the first 380,000 years and before them is calculable, derivable, testable through indirect signatures even when direct observation is impossible. Gravitational waves pass through the early universe without scattering the way light does. They carry information from times and conditions that light cannot reach. The equations of general relativity, quantum mechanics, and thermodynamics do not contain a clause that says, "Stop here. This is where description ends." They keep going backward, and what they produce when you run them backward past the point we can directly observe is where this story begins. The textbook version of the Big Bang presents it as the absolute beginning, the moment before which the word before has no meaning. Time started, space started, everything started, full stop. That framing is clean, it is simple, it fits on a timeline, and it is, at minimum, incomplete and possibly wrong in a fundamental way. Einstein's general relativity, when pushed all the way back to that starting point, produces a singularity, infinite density, zero volume. The equation breaks, and when an equation breaks, it does not mean you have found the answer. It means you have found the edge of the theory's validity. Physicists know this. The singularity is not a description of what actually happened. It is a signal that general relativity alone cannot describe what actually happened. That gap between what the equations produce and what physically occurred is not closed. It is open, actively open, with serious researchers on multiple sides and no consensus on the answer. Some argue the universe bounced from a previous contraction. Some argue it condensed out of an eternally inflating vacuum. Some argue it was born from the collision of structures in dimensions we cannot directly detect. They cannot all be right, but they are all doing real physics, and the question driving all of them is the same one that most science communication treats as settled or unanswerable. It is neither. What came before the Big Bang is the most important open question in cosmology right now. The field is quietly divided on whether we can ever answer it, and that division is itself a scientific story worth understanding. And the fact that most people have never heard that question treated as a serious scientific problem is not because the science is not there. Here is the thing about the Big Bang that nobody tells you up front. We have never actually seen it. Not directly, not even close. Every image, every visualization, every documentary that shows you a brilliant point of light exploding outward into everything, that is a reconstruction, an inference. What our instruments actually detected is something far more subtle and far more interesting, and the gap between what we detected and what we are claiming to know is where this entire question lives. In 1965, two radio engineers at Bell Labs named Arno Penzias and Robert Wilson were trying to calibrate an antenna. They kept picking up a faint background noise coming from every direction at once. They could not eliminate it. It was not equipment interference. It was not local radio signals. It was the same in every direction, at every hour, in every season. What they had found, without looking for it, was the cosmic microwave background, the CMB. It is a faint glow of microwave radiation that fills the entire observable universe uniformly, and it is the oldest light our instruments can detect. Here is why that matters. In the very early universe, matter was so dense and so hot that photons could not travel freely. A photon is a particle of light. In the first 380,000 years after the Big Bang, every photon that tried to move through space was almost immediately absorbed or scattered by the surrounding plasma. The universe was, in practical terms, opaque. Light could not get through. So any photons from that era never reached us intact. They were absorbed long before any instrument could catch them. At around 380,000 years, the universe had cooled enough that electrons and protons combined to form neutral hydrogen atoms. Suddenly, photons could travel freely. The universe became transparent, and those first free photons have been traveling through space ever since, stretched by the expansion of the universe from visible light down into microwave frequencies. That is the CMB. That is what Penzias and Wilson found. That is the wall. And it is a genuine wall. Everything before 380,000 years is, from a photon-based observational standpoint, inaccessible. Optical telescopes cannot see through it. Radio telescopes cannot see through it. No instrument that detects electromagnetic radiation reaches past it. The Planck satellite mapped the CMB with extraordinary precision. The James Webb Space Telescope sees galaxies forming hundreds of millions of years after the Big Bang, but neither of them, nor any instrument like them, will ever see the first 380,000 years directly, not through light. Now here is the question those textbooks skip. Does the wall mean nothing is there? Does inaccessible to our current instruments mean physically unknowable? No. And here is my position on that distinction. It is the single most important distinction in this entire discussion. Absence of direct observation is not absence of physics. The math does not stop at the wall. The equations that govern how matter and energy behave do not have an exception for the first 380,000 years. We can calculate what the conditions were. We can model what processes were occurring. We can work backward from what we observe now and infer the state of the universe at times we cannot directly see. Scientists have done this for decades. It is not speculation. It is inference from known physics, the same method that lets us calculate the internal temperature of the sun without sending a probe into it. But inference from known physics has limits. You are always dependent on your model being correct. If your model of what the universe was doing before the wall is incomplete, your inferences are incomplete. And there is a second way to get information from before the wall that does not depend on light at all: gravitational waves. Unlike photons, gravitational waves are not absorbed or scattered by the dense plasma of the early universe. They pass through matter almost entirely unimpeded. A gravitational wave generated in the first fraction of a second after the Big Bang would have traveled through the opaque plasma, through the recombination epoch, through 13.8 billion years of cosmic expansion, and it would still be detectable today if our instruments were sensitive enough to find it. The signal would be faint, stretched, carrying the imprint of physics that operated before any light we can see was produced. This is not theoretical possibility. This is why the next generation of gravitational wave observatories, instruments like LISA and the Einstein Telescope, are being built. The wall is real, but it is only a wall for light. Something else gets through. What comes before the wall is not silence. It is a signal in a different language, one we are only now building the instruments to read. The light stops at 380,000 years, but the physics does not, and that difference is where everything in this story begins. Before you can understand what might have existed before the Big Bang, you have to focus on a single critical point, and that is all. Everything that follows emerges directly from this foundation. General relativity, Einstein's theory of gravity, is the most tested theory in the history of physics. It predicted the bending of light around the sun. It predicted gravitational waves decades before we had instruments sensitive enough to detect them. Every GPS satellite in orbit runs a timing correction based on its equations. The theory works. That is not in dispute, but every theory has a boundary, a set of conditions beyond which the equations were never designed to operate. And at the Big Bang, general relativity hits its boundary hard. In 2001, a physicist named Martin Bojowald did something simple and got a result that should have been impossible. He took the equations of loop quantum gravity and applied them to the early universe, not to add complexity, not to propose a new model of cosmic origins. He was testing whether the framework held under extreme conditions. It did not just hold. It produced something the standard equations had never produced before. It produced a universe that existed before ours. Here is what loop quantum gravity actually is, because this matters. General relativity treats space and time as a smooth, continuous fabric. Quantum mechanics treats everything else as discrete, granular, broken into irreducible minimum units. The problem is that these two frameworks, both extraordinarily accurate in their own domains, are fundamentally incompatible with each other. Physicists have known this for decades. Loop quantum gravity is one attempt to resolve that incompatibility. It applies the logic of quantum mechanics directly to the structure of spacetime itself. Space, in LQG, is not a smooth fabric. It is a network. It has a minimum unit, a smallest possible chunk below which the concept of space ceases to have meaning. That unit is called the Planck area. It is unimaginable, I-small, but it is not zero. That distinction is everything. Now go back to the singularity problem. The previous section established that general relativity, run backward through cosmic history, produces a singularity. Volume collapses to zero. Density climbs to infinity. The equations break. The reason they break is that general relativity assumes space can be compressed without limit. There is no flaw. In loop quantum gravity, there is a flaw. Space cannot be compressed below the Planck scale. The granularity of spacetime itself acts as a resistance. And when Bojowald ran the LQG equations backward through the Big Bang, the compression hit that floor and stopped. The singularity did not appear. What appeared instead was a bounce. Think of it like a spring. Classical physics, if you compress a spring with enough force, eventually gives you a mathematical point with no volume and infinite pressure. That is physically meaningless, and everyone knows it. The molecular structure of the spring sets a real lower limit. You cannot compress it past the point where its actual physical structure resists. Loop quantum gravity does the same thing for space itself. The quantum geometry of spacetime has a structure. That structure resists. And at the point where general relativity would produce a singularity, LQG produces a bounce. What does the bounce mean? It means that the contracting phase did not end in annihilation. It ended in a reversal. A previous universe that had been collapsing for billions of years reached that minimum volume, that quantum gravitational floor, and the collapse converted into expansion. The energy that had been driving the contraction became the energy that drove the expansion. What we observe as the Big Bang, the initial moment of our universe's rapid outward expansion, was not a creation event. It was a transition point, the end of one universe's collapse and the beginning of another universe's expansion. Our universe. The implication is direct. Something was here before us, not metaphorically, mathematically. Now here is what LQG actually says about the universe on the other side of that bounce. The previous universe was not identical to ours. The bounce does not preserve everything. Certain quantum information about the geometry of the contracting universe crosses the transition. Bojowald's early work suggested that some properties of the previous universe, specifically aspects of its quantum state, leave imprints on the initial conditions of our own. How large was the previous universe? How long did it contract before reaching the bounce? What was its geometry? These are not answered definitively by the current framework, but the framework produces finite, calculable quantities where general relativity produces infinities. That is a fundamental difference. The maximum energy density at the bounce point is enormous, something like 10 to the power of 96 kilograms per cubic meter. That number is so large it strains comprehension, but it is a number. It is not infinity. And a physics equation with a real number as its answer is a different kind of equation, and one that produces infinity. It is an equation you can work with. Why did this not immediately overturn everything in cosmology? That is the right question to ask. The honest answer is that loop quantum gravity remains one of several competing quantum gravity frameworks, none of which has yet produced a clear, confirmed observational prediction that distinguishes it from alternatives. String theory is another approach. They produce different mathematical structures and different descriptions of what happens at Planck-scale energies. The community has not reached consensus. And the energies involved in the Big Bounce are so extreme, roughly 1 trillion times beyond what any particle accelerator can produce, that direct experimental confirmation is not currently possible. So the result sits in the literature, peer-reviewed, mathematically rigorous, unrefuted, and largely absent from the public conversation about cosmic origins. Here is what the public conversation usually says. The Big Bang was the beginning. Full stop. That framing is not wrong in every context, but it is incomplete in a way that matters. It treats the singularity as an answer rather than a signal that the equations broke. Loop quantum gravity replaces the singularity with a transition point and shows a contracting universe on the other side. Martin Bojowald's equations did not produce a beginning. They produced a history, a previous universe, collapsing toward the same laws of physics we live inside today, reaching a quantum gravitational minimum, and bouncing outward into what became everything we have ever observed. The equations did not stop at the Big Bang, and what they showed on the other side was not nothing. Roger Penrose is not asking the question carefully, he is asking it precisely. There is a difference. Careful questions leave room for comfortable answers. Precise questions do not, and what Penrose has built over the last 2 decades is one of the most precise and uncomfortable arguments in modern cosmology. Penrose won the Nobel Prize in Physics in 2020, not for this work, for proving, mathematically, that black holes are a real and inevitable consequence of general relativity. That is the body of work that earned him the prize. The reason that matters here is simple. When Penrose speaks about the structure of the universe at its largest scales, he is not operating outside his area of expertise. He is working at the center of it. This is not a physicist who wandered into cosmology from somewhere else. This is one of the people who built the mathematical foundation the field stands on. His model is called Conformal Cyclic Cosmology. The name is technical, but the argument behind it is something you can follow without the mathematics, and it starts with a question about the far future. Think about what this universe eventually becomes. Stars burn through their fuel and go dark. Galaxies drift apart as space expands. Black holes consume whatever falls into their reach. Over timescales so long they are almost meaningless to state, even the black holes evaporate through Hawking radiation, releasing their mass back as photons and gravitational waves. What is left at the absolute end of everything is a universe containing essentially nothing with mass, just light, just radiation, just gravitational waves moving through an empty, dark, still expanding space. Now here is where the argument turns. Mass is what gives the universe a sense of scale. Without mass, there are no rulers, there are no clocks, there is nothing to measure distance against, nothing to measure the passage of time against. A universe with no mass has lost the ability to define what big or small even means. In the branch of mathematics called conformal geometry, the structure of such a universe, its shape, its causal relationships, the way events connect to each other, is described by a conformal factor. And when you strip out the mass, when you let the scale go to infinity, the conformal structure of a universe at its infinite future and the conformal structure of a universe at its absolute beginning look mathematically identical. Penrose's argument is that they are not just similar, they are the same. The infinite future of one universe and the Big Bang of the next universe can be mathematically identified with each other. The end of one aeon, as he calls it, is the beginning of the next. The universe does not bounce, it does not collapse and re-expand. It simply continues, and what looks like a boundary, a Big Bang, is just a surface where the geometry of a dying universe transforms into the geometry of a newborn one. What this means is direct. Before our Big Bang, there was an entire previous universe. It lived through its own expansion, its own stellar era, its own long cooling silence. Its black holes formed and eventually evaporated. Its last photons spread out across its enormous dark volume. And then, as the scale of that universe became unmeasurable, as mass disappeared and conformal equivalence took over, that universe's infinite future became our beginning. We are not the first aeon, we are the next one. That is already an extraordinary claim. But Penrose did not stop there. He made a prediction, a testable one. If the previous aeon had black holes, and it did, because every universe with matter eventually forms black holes, Then those black holes evaporated at the end of the previous aeon, and that evaporation released enormous pulses of energy. Those pulses passed through the conformal boundary between aeons, and they should have left marks, specific, detectable marks, circular patterns in the cosmic microwave background radiation, the oldest light we can observe. Penrose and his colleagues called these marks Hawking points, named after Stephen Hawking, whose work on black hole evaporation the prediction depends on. Think about what that means. Penrose is not just proposing a theoretical framework for a universe that came before ours. He is saying that the previous universe left fossils, and that those fossils are visible right now in data we already have. The cosmic microwave background has been mapped in extraordinary detail. The WMAP satellite mapped it. The Planck satellite mapped it with even higher resolution. If Penrose is right, then somewhere in those maps are faint concentric rings, slightly quieter than the surrounding radiation, marking the spots where the last black holes of the previous universe finished dying. This is what separates conformal cyclic cosmology from most pre-Big Bang frameworks. It does not just propose that something existed before. It says here is what that something left behind. Here is where to look. Here is what the data should show if the model is correct. In 2010, Penrose and the Armenian physicist Vahe Gurzadian published a paper saying they had found exactly that: concentric rings of anomalously low temperature variance in the CMB data. Multiple rings. At a statistical level, they argued was significant. The imprints of black hole evaporation events from the aeon before ours, written into the oldest light in our universe. The response from the field was not silence. It was not the institutional shrug that followed the Simonetti-Frank paper on ancient civilizations. It was loud, fast, and pointed. Multiple teams published rebuttals within months. The debate became one of the most actively contested arguments in observational cosmology over the following years. What he found in the data and what the field did with it is the part that should make you stop. When the paper came out, the field did not ignore it. That is worth being precise about. In 2010, Roger Penrose and Armenian physicist Vahe Gurzadian submitted a paper claiming they had found something in the WMAP satellite data. Not a theoretical prediction, not a model output, an actual signal sitting in the oldest observable light in the universe. Concentric rings, circular regions where the temperature variance in the cosmic microwave background was anomalously low, arranged in patterns that standard cosmology had no reason to produce. Their interpretation was direct. These rings were imprints left by collisions between supermassive black holes in the previous aeon. When those black holes merged, they released gravitational wave pulses of enormous energy. Those pulses passed through the Big Bang transition intact and left faint circular marks in the CMB. That is what Penrose and Gurzadian said they found. The response from other researchers was fast, and it was critical. 3 separate teams published papers within weeks. All 3 reached the same conclusion. The patterns were not statistically significant. The claim, these groups argued, rested on a comparison between the WMAP data and simulated CMB maps. And when you generate those simulated maps correctly, using the standard cosmological model, the same concentric ring patterns appear. The signal was not anomalous. It was exactly what you would expect from random fluctuations in a standard Big Bang universe with no previous aeon. One team used 5 different statistical methods. None of them found evidence that the rings in the real data were different from the rings in the simulated data. That is a serious counterargument, not a dismissal, a technical rebuttal with specific methods attached to it. Penrose and Gurzadian pushed back. Their response was also technical. The simulations the other teams used, they argued, were not built the correct way. The standard CMB simulations assume a particular power spectrum for the temperature fluctuations, and that assumed spectrum affects whether the rings appear. If the simulations already encode a version of the answer, then finding that the data matches the simulations tells you less than it appears to. The comparison is circular, that is not an evasion, it is a methodological objection, and it has not been fully resolved. What does that mean? It means the field has 2 positions on the table, both backed by published analysis, and no clean verdict. By 2018, Penrose had pushed the analysis further. Working with Daniel Ahn, Christoph Meissner, and others, he identified what he called Hawking points. These are not the concentric rings from the 2010 paper. They are something more specific. Points of anomalously high temperature in the CMB, surrounded by a slight halo of warmer radiation. The proposed source is Hawking radiation. At the very end of the previous aeon, after all matter has fallen into black holes, and those black holes have spent trillions upon trillions of years slowly evaporating, the final bursts of Hawking radiation from the largest black holes would produce concentrated energy releases. Those bursts, Penrose argues, would leave faint hot spots in the CMB of the next aeon. His team reported finding them, multiple candidate points, statistically significant above the background, they claimed, at the level of roughly 3 sigma. Again, other researchers looked at the same data and disagreed. The hotspots exist. That is not the dispute. The dispute is whether their distribution and intensity exceed what a standard cosmological model would produce by chance. And again, the answer depends on how you build the comparison set. This is where the technical argument lives. It is not a simple disagreement. It is a deep statistical question about how you construct a null hypothesis when the thing you are testing against is itself a model built on assumptions. Here is what gets lost in that back and forth. Penrose did not speculate. He did not suggest that the previous aeon might leave some kind of general trace. He produced a specific quantitative observational prediction, a precise type of signature in a precise location in the data, derivable from first principles within his framework. Then he went and looked for it. Then he reported finding it. Then other researchers tried to replicate the finding and argued it did not survive scrutiny. That is not a failure. That is science working as it is designed to work. The structure of the inquiry is correct regardless of how the statistical dispute resolves. What the field has not done is treat conformal cyclic cosmology as a framework that deserves a dedicated search effort. The papers get cited, the objections get published, the argument loops. No major observatory time has been allocated to specifically test the Hawking point prediction with the precision the question requires. The Planck satellite produced a CMB map far more detailed than WMAP. Independent analyses of the Planck data for CCC signatures exist, but remain contested on the same statistical grounds. The pattern is familiar: a formal, testable prediction from a serious researcher. A technical debate that has been running for over a decade without resolution, and no institutional push to gather the data that would settle it. The disagreement is real and legitimate, but the question it is fighting over is whether we have already found the imprint of the universe that came before ours in the oldest light we can observe. There is a version of this story where the question of what came before the Big Bang has a very simple answer: not a bounce, not a dying universe whose geometry folds into a new one. Something simpler and in some ways more unsettling. The answer is that before our Big Bang, the same process that created our Big Bang was already running. It had been running. It will keep running. Our universe did not emerge from silence or from the collapse of something that existed before it. It emerged from an ongoing process that has no edge and no start, and our Big Bang was simply one local event inside that process. This is the idea behind eternal inflation, and it is not a fringe position. It is the near-inevitable consequence of the most successful model of the early universe that physics has produced. To understand eternal inflation, you need to understand what inflation itself is. In the early 1980s, physicists including Alan Guth, Andre Linde, and others were working on a problem that the standard Big Bang model could not solve. The universe looks the same in every direction, not roughly the same. Remarkably, precisely the same, even in regions that could never have been in contact with each other given the known age of the universe. Points on opposite sides of the sky that are too far apart to have ever exchanged information somehow arrived at the same temperature, the same density, the same structure. The standard model has no explanation for that. Inflation does. The proposal is that in the universe's earliest moments, a field of energy called the inflaton drove a period of exponential expansion. The universe doubled in size, then doubled again, doing this at least 80 times in a fraction of a second. Everything we observe today was compressed into a region so small that quantum-scale uniformity could be established before inflation stretched it out to cosmic scale. The horizon problem disappears. The flatness problem disappears. Several other structural puzzles in cosmology dissolve along with them. Here is the problem. Inflation works. The predictions it makes about the structure of the cosmic microwave background match what we observe with extraordinary precision. That success is what makes the side effect so difficult to dismiss. In virtually every mathematical implementation of inflation, the inflaton field does not stop everywhere at once. It stops locally, in isolated regions, driven by quantum fluctuations that push the field below the threshold needed to sustain expansion. But in the surrounding space, the field keeps going. It keeps driving exponential expansion. And because exponential expansion is so fast, the regions where inflation has not stopped grow larger faster than the regions where it has ended. The inflating space is always winning. It never depletes itself. It never reaches a final edge. What does that mean exactly? It means our universe formed the way a bubble forms in boiling water. The vacuum energy in our local region of the inflating space underwent a quantum fluctuation. Inflation ended here. That transition released energy, produced a hot, dense plasma, and what followed was the expansion and cooling we call the Big Bang and the subsequent history of our universe. Meanwhile, outside our bubble, inflation kept going. Other fluctuations happened elsewhere. Other bubbles formed. Other universes, each with its own physics, its own constants, its own history, expanding inside the same eternally inflating background. This is the multiverse, not a science fiction concept, a mathematical consequence. Alan Guth, who developed the original inflationary model, has stated his position plainly. If inflation is correct, the multiverse is almost certainly real. The two are not separate ideas. The multiverse follows from inflation the way compound interest follows from an interest rate. You do not get one without the other unless you construct a very careful and somewhat artificial version of inflation specifically designed to avoid the conclusion, and even then the problem tends to return. Now here is the question the textbooks skip. If inflation produces an eternally inflating space, and our universe is one bubble inside that space, what does that say about what came before our Big Bang? The answer is direct. Before our Big Bang, the inflating vacuum existed. It was expanding. Other bubbles may have already formed inside it. The process was running. Before that moment, the same was true. The inflating space does not require an origin. No current model of eternal inflation produces a beginning for the inflating vacuum itself. It extends backward without a starting point that the mathematics demands. What we call the beginning of everything was not a beginning at all. It was a local transition in a structure that had no need to begin. This is where the institutional response becomes worth examining. The multiverse is simultaneously the most natural consequence of the most successful theory in early universe cosmology and the most disputed idea in theoretical physics. Critics, including Paul Steinhardt, who we will return to, argue that a framework which generates infinite universes with every possible set of physical constants makes no testable predictions. If everything is possible somewhere, nothing is specifically predicted anywhere. The inflationary multiverse, in this view, is not science. It is a mathematical landscape that can absorb any observation without ever being constrained by one. That critique is serious. It comes from serious physicists, and it does not resolve easily. What does not get disputed is the chain of logic that produces the result. Inflation is real. The evidence is strong. Eternal inflation is the natural consequence. The multiverse follows. And if the multiverse is real, then before our Big Bang was not an edge, not a wall, not an absence of anything. It was a vast inflating space producing beginnings the way our sun produces photons, continuously, in all directions, without pause or plan or end. Our Big Bang was a local event in a structure that never started and, by the current mathematics, will never end. String theory does not produce one version of before the Big Bang. It produces several, and one of them is so different from everything else covered in this series that it deserves its own treatment. Not because it is the leading model, it is not, but because it starts from completely different assumptions and arrives at a completely different picture of what the Big Bang actually was. The model is called the Ekpyrotic scenario. The name comes from the Greek word for conflagration. That choice is not accidental. Here is the core claim. What we call the Big Bang was not a creation event, it was a collision. Two vast, multidimensional objects struck each other, and the energy released from that impact is what became the hot, dense fireball we observe in our earliest cosmological data. To understand why that is even a coherent physical claim, you need to understand something about what string theory actually says about the structure of reality. In standard physics, reality has three spatial dimensions. String theory requires more. The exact number depends on the version, but the most developed formulation requires 10 spatial dimensions plus time. We experience 3 of those dimensions. The rest are compactified, curled up at scales so small they have no effect on everyday physics, but they are there in the mathematics, and objects can exist in those extra dimensions. Those objects are called branes, short for membranes. A brane is an object that extends through some number of dimensions, the way a sheet of paper extends through 2. Our entire observable universe in the Ekpyrotic model sits on one such brane, a 3-dimensional surface embedded in a higher dimensional space. Think of it like a thin film floating in a deeper medium. Everything we can see, touch, or measure exists on that film. The extra dimension sits perpendicular to it, invisible to us because we are confined to our brane. Now, there is another brane, nearby in that extra dimension, separated from our brane by a gap that is genuinely tiny by cosmological standards, yet completely inaccessible to us because we cannot move perpendicular to our own brane. That second brane has mass, so does ours, and gravity, unlike everything else in string theory, leaks into the extra dimensions. The 2 branes are attracted to each other gravitationally across that gap. They move toward each other, slowly, over an enormous timescale, almost imperceptibly, across what could be trillions of years. The 2 branes fall toward each other through the extra dimension, and then they collide. The collision converts the kinetic energy of both branes into heat, radiation, and matter. The temperature spikes. Particles flood into existence. What you get, on our brane, looks exactly like a hot, dense fireball expanding outward from an initial moment. It looks, in other words, like the Big Bang. Not because a singularity formed, not because the universe emerged from nothing, but because 2 large objects hit each other and the energy had to go somewhere. Paul Steinhardt at Princeton and Neil Turok at Cambridge developed this model in 2001. Both of them had previously worked on inflation. Both concluded that the standard inflationary picture had unresolved problems. The Ekpyrotic scenario was their alternative. In their version, the branes do not simply collide once. After the collision, they bounce apart. The cycle resets. Over another vast timescale, they fall toward each other again. The process repeats. Each collision is another Big Bang. Each separation is another cosmic expansion. The universe does not have a beginning in this model. It has a rhythm. Here is where this becomes scientifically interesting rather than just mathematically interesting. The Ekpyrotic model makes a specific prediction about gravitational waves. Inflation also makes a prediction about gravitational waves. The 2 predictions are different. In the inflationary model, the exponential expansion stretches quantum fluctuations into a gravitational wave background with a particular spectrum, a slight tilt toward longer wavelengths. The Ekpyrotic model, because the collision mechanism is fundamentally different, predicts a gravitational wave background that is nearly flat. The tilt is essentially absent. These 2 spectra can, in principle, be distinguished by sensitive enough detectors. Future gravitational wave observatories, including LISA and next-generation GROW, UND-based instruments will be measuring this background. If inflation is right, they should see the tilt. If they see a flat spectrum instead, the Ekpyrotic model gains serious ground. What is the current scientific status? The Ekpyrotic scenario is a minority position. Most working cosmologists favor inflation, but it is a published, peer-reviewed, mathematically rigorous minority position developed by serious physicists with strong records. It has not been ruled out. The gravitational wave background it predicts has not been measured. The test has not been run. That matters because a model that makes a testable prediction and has not been tested is not a failed model. It is a waiting one. The reason it is worth sitting with this is not that it is probably correct. It may not be. The reason is what it represents. It is a framework in which the Big Bang is the result of a physical process that preceded it. There was something before, something structured, something massive. 2 branes slowly falling toward each other across an extra dimension, and when they finally collide, the energy of that impact becomes everything we have ever observed. Here is the question that sits underneath all the models and all the data and all the debate. Not which model is correct, not whether the bounce happened or the branes collided or the inflation never stopped. The deeper question, the one that makes all the others harder than they already look. Did time exist before the Big Bang at all? And if it did not, What does that do to every answer we have been building toward? In the 1960s, two physicists named Bryce DeWitt and John Wheeler tried to write down the fundamental equation of quantum gravity, the equation that would describe the quantum state of the entire universe. They produced something that works, at least formally, and physicists still use it today. It is called the Wheeler-DeWitt equation. Here is what almost nobody mentions when they bring it up. The equation has no time variable in it, not a hidden one, not an approximated one, none. Time does not appear as a fundamental quantity in the equation that is supposed to describe the quantum state of everything that exists. Think about what that means for a moment. Every equation in physics you have ever encountered, even informally, involves time. Position changes over time. Energy evolves over time. Particles interact at specific moments in time. The whole architecture of physics is built on the assumption that time is there, that it is real, that things happen in it. The Wheeler-DeWitt equation looks at the universe as a whole and time drops out entirely. This is not a technical footnote buried in a footnote about something else. This is the central equation of quantum cosmology, and it has no time in it. So what is going on? The most serious interpretation is that time is not fundamental. It does not exist at the deepest level of physical reality. What we experience as time, the sense that there is a before and an after, that causes precede effects, that one moment follows another, may be something that emerges from more basic quantum processes. The same way temperature emerges from molecules. No individual molecule has a temperature. Temperature is a property that appears when you have enough molecules collectively moving and colliding. One atom has kinetic energy. 1,000,000,000,000 atoms have a temperature. The property is real. It is measurable, but it is not fundamental. It lives at a higher level of description. Time may work the same way. Julian Barber has spent decades developing exactly this argument. His position is direct. Time is an illusion. Not an illusion in the dismissive sense, not something that does not matter, but an illusion in the precise sense that it is a feature of our experience that does not correspond to anything in the fundamental structure of reality. What we call the flow of time, what we call the present moment, what we call change, these are things that emerge from the configuration of matter and energy in the universe, from our particular position inside the quantum state, not features of the quantum state itself. Now here is where this becomes a problem for every question we have been asking, because every model of what came before the Big Bang, the Big Bounce, conformal cyclic cosmology, eternal inflation, Brane collisions, every single one of them assumes that time is a coherent concept to apply to that question. They all involve a sequence. A universe contracts and then bounces. A previous aeon ends and a new one begins. An inflating vacuum persists and then locally stops. All of that language requires time to be real and fundamental. It requires a before and an after. If time is emergent, then the question of what came before the Big Bang may not be a question with an answer, not because the answer is unknowable, because the question itself may be malformed. It would be like asking what happened before existence began. The word before only has meaning if time is already operating. If time did not exist in any meaningful sense at or before the conditions that produced the Big Bang, then there is no before to point at. Here is my position on this. The Wheeler-DeWitt result is genuine. The timelessness of the equation is not a bug. It is telling us something real about the structure of the universe at the level where quantum mechanics and gravity both apply. Whether that means time is fully emergent or just that our description of it needs refinement is something the field has not settled. But the honest answer to every question about what came before the Big Bang has to carry this caveat. Every model, every bounce, every cyclic aeon is built using time as a scaffolding. And the most fundamental equation we have suggests that scaffolding may not be load-bearing. The causal set approach to quantum gravity offers one way through this. In that framework, what we call time is replaced by causal ordering, a structure of events where some things simply come before others, not in a measured sense, but in a structural one. Time without a clock, sequence without duration. It is a strange idea, but it allows the equations to continue past the classical Big Bang boundary without requiring that time existed in any conventional sense before it. What the math is actually saying is that we are asking questions about the universe's origin using a concept, time, that the universe's most fundamental description does not recognize as basic. And if time is not fundamental, then asking what came before the Big Bang is like asking what is north of the North Pole. Not a question that has an answer, but a question that reveals the limits of the framework you are using to ask it. Long before anyone had the mathematics to model the Big Bounce or eternal inflation, people were already arriving at a specific answer to the question of what came before. Not a random assortment of answers, not scattered, unrelated guesses. The same answer, repeated across cultures that had no contact with each other, separated by oceans and centuries and entirely different intellectual traditions. That pattern is worth looking at directly. Hindu cosmology describes the universe as cycling through enormous spans of creation and destruction. The basic unit is a kalpa, a single day in the life of Brahma, lasting roughly 4.3 billion years. A full Brahma cycle runs to 311 trillion years. After each cycle, the universe dissolves. Then it begins again. This is not a minor feature of the tradition. It is central. The cosmos is not created once. It is recreated continuously. And what looks like a beginning is always a transition out of something that came before. Buddhist cosmology goes further in a specific direction. There is no absolute beginning. The question of a first cause is rejected not as unanswerable but as malformed. The universe has always existed in some form. Time has no starting edge. Medieval philosophers in India were teaching versions of this systematically, building logical frameworks for endless cosmic cycles, centuries before the word cosmology existed in its modern sense. Ancient Chinese cosmology framed creation as multiplicity emerging from unity, order arising from chaos, a single undifferentiated source producing the structured complexity we observe. If you translate that into modern terms, the parallel to inflation theory is not subtle. A featureless initial state, governed by a single field, expanding and differentiating into the structured universe we now measure. Same basic architecture, different vocabulary. Now here is what needs to be said clearly, because this is where overclaiming becomes a real risk. None of this is evidence, not for the Big Bounce, not for eternal inflation, not for any specific physical model. Ancient cosmological frameworks were not doing physics. They were doing something else: philosophy, theology, systematic reflection on the nature of existence, and the fact that they arrived at cyclic structures does not validate those structures scientifically. The math has to do that work on its own, and the math does not need the ancient frameworks to support it. Loop quantum gravity stands or falls on its equations, not on the Brahma cycle. But the convergence is still worth naming as a fact, because facts deserve acknowledgement. Cultures with no shared intellectual history, no common texts, no mechanism for transmitting specific cosmological ideas across the distances and timescales involved, they all arrived at the same structural intuition: that the universe cycles, that what looks like a beginning is a transition, that the cosmos has no absolute first moment. Modern physics spent decades building mathematical frameworks sophisticated enough to reach the same conclusions, and when it got there, it found that certain ancient traditions had already drawn the same map, roughly, in different language, with no instruments. There are two ways to interpret that. One is that human minds, when they sit with the question of origin long enough, tend to find cyclic answers because cyclic systems are stable and self-contained and aesthetically satisfying. And that tells us something about cognition, not cosmology. The other interpretation is that the question itself has a structure that tends to push careful reasoning towards certain conclusions, that the logic of origins, when followed honestly, resists the idea of a true beginning, and that ancient thinkers and modern physicists were both responding to that same logical pressure from the problem itself. Neither interpretation can be verified. That is part of why this pattern is interesting rather than decisive. It does not resolve anything. It does not point at a specific model or confirm a specific prediction. What it does is raise a narrow, honest question about the nature of the convergence. Whether minds working independently on the same problem tend to produce similar answers because the problem constrains the answer space, or because we all share the same cognitive architecture and that architecture has its own biases. The question is whether that convergence tells us something about the problem or just something about us. Here is what separates the serious models from the speculation. Testable predictions. A model that cannot be tested is not wrong. It is something worse than wrong. It is untethered, and the question of what came before the Big Bang has spent decades being dismissed precisely because it seemed untestable by definition. That dismissal is no longer fully accurate. The models are making specific predictions. The instruments to test them are either operational or under construction, and the gap between what we can currently see and what we will be able to see inside the next decade is where this entire conversation is about to change. Start with gravitational waves. Photons cannot travel freely through the early universe. The plasma is too dense, too hot. Light gets absorbed and rescattered constantly. That is why the CMB Wall exists at 380,000 years after the Big Bang. Gravitational waves do not have that problem. They pass through matter almost without interaction. A gravitational wave produced in the first fraction of a second after the Big Bang would still be traveling today, largely unchanged. That is not a hope. That is a consequence of how gravity works. What this means is direct. If inflation happened, it produced gravitational waves. If the Ekpyrotic model is correct and two branes collided, that collision produced gravitational waves. Different processes, different spectra, measurable difference, in principle. Inflation predicts a primordial gravitational wave background with a specific tilt, more power at longer wavelengths. The Ekpyrotic model predicts something close to flat, no tilt, or nearly none. LISA, the Laser Interferometer Space Antenna, is scheduled for launch in the 2030s. The Einstein Telescope is in planning. Both are designed to detect signals that current ground-based detectors cannot reach. If the primordial gravitational wave background is there, these instruments will find it, and the shape of that background will tell us which model is closer to correct. That is not inference. That is a real observational target with a real instrument going after it. So now here is the thing about the CMB. We already have data, Planck satellite data, the most precise map of the cosmic microwave background ever produced. And that data contains anomalies, not small statistical noise, large-scale anomalies. A cold spot in the southern sky, a suppression of power at the largest angular scales, an alignment between certain temperature patterns that standard cosmology does not predict. The textbook model says these fluctuations should be random. They are not entirely random at the largest scales. Why is that not a bigger story? Researchers have been noting it in publications for over a decade. Some argue the anomalies reflect pre-inflationary physics, structure that was imprinted before inflation began, which survived because the scales were large enough to AVO, ID being washed out. If that is right, the CMB is already carrying information from a period before what we typically call the Big Bang era. We just have not agreed on how to read it. Penrose's Hawking points sit inside this same debate. Circular patterns in the CMB with anomalously low temperature variance. His interpretation is that these are imprints of black hole evaporation events from the previous aeon, gravitational pulses that passed through the conformal boundary between universes and left faint rings in the oldest light we can observe. The statistical dispute is ongoing. Other teams say the patterns are not significant when you compare them to simulated maps. Penrose's group says the simulations are built on assumptions that beg the question. That argument has not been resolved. But notice what has happened. A specific, falsifiable prediction was made. A specific location in existing data was identified. A specific method for evaluating it was proposed and disputed. That is what science is supposed to produce. The disagreement about whether the evidence holds up does not change the fact that the framework generated a testable claim. More CMB data is coming. The Simons Observatory and CMB-S4 experiments will produce maps with sensitivity that Planck could not achieve. If the patterns are real, better data will confirm them. If they are noise, better data will show that too. The third line of evidence involves primordial black holes. If the universe passed through a previous phase, a contracting phase in the Big Bounce framework, or a previous aeon in conformal cyclic cosmology, certain black holes could be relics of that transition. Not black holes formed from collapsing stars. Black holes formed from the density fluctuations of an earlier universe, surviving the bounce and appearing in ours as anomalous compact objects. Here is why that matters. Dark matter is still unidentified. We know it exists from its gravitational effects. We have not found the particle. Primordial black holes are a candidate. A fraction of the dark matter could be primordial black holes left over from a pre-Big Bang phase. Current microlensing surveys are constraining the mass ranges W. Here, primordial black holes can exist. The constraints are getting tighter. If primordial black holes at certain mass ranges are eventually found in abundance, and no stellar formation process accounts for them, that is a signal worth examining against cyclic models. Here is my position on where all of this stands. The honest answer is that no single observation has yet confirmed any pre-Big Bang model. The gravitational wave background has not been measured at the frequencies these models require. The CMB anomalies remain statistically contested. The primordial black hole evidence is indirect at best. None of that means the models are wrong. It means we are still at the point where the instruments are catching up to the questions. That is a specific moment in a field. It does not last. Within the next decade, the gravitational wave detectors coming online will either see the background signature inflation predicts, or they will see something else entirely. And that something else is where the pre-Big Bang physics lives. What happened after multiple serious physicists formally published models of what came before the Big Bang? The papers came out, other researchers cited them, review articles acknowledged the frameworks, and then the funded research programs, the dedicated institutional efforts, the coordinated attempts to test these models against new data, those largely did not follow. Not because the work was obviously wrong, because the work pointed somewhere that the field, as currently organized, is not well equipped to go. That is worth sitting with. When a credentialed physicist publishes a peer-reviewed model with real mathematical structure, the expected response is engagement. Other researchers test it, they challenge the assumptions, they look for observational predictions and try to break them. That process is how science protects itself from bad ideas. It is also how good ideas get refined into something testable. When this process fails to unfold, such an omission is deeply meaningful. It signals what the field has collectively determined to recognize as legitimate. Here is the thing about the question of what came before the Big Bang. It is not being ignored because no one has worked on it seriously. Loop quantum gravity, conformal cyclic cosmology, the Ekpyrotic model, eternal inflation. These are not blog posts. These are decades of published, peer-reviewed theoretical physics from researchers at major institutions. The work exists. It is real. And yet the direct question, what was here before our universe began, sits at the edge of what cosmology, as an institution, treats as a fundable, serious primary research priority. Why? Part of the answer is hard and honest. The tests are far away. Gravitational wave detectors capable of distinguishing between inflationary and pre-bounce signatures do not fully exist yet. CMB measurements sensitive enough to resolve the anomalies Penrose identified are still being built. When the observational tools are a decade or more from maturity, it is genuinely difficult to organize a research program around them. That is not conspiracy. That is resource allocation under uncertainty. But part of the answer is less comfortable. Paul Steinhardt is one of the physicists who co-developed the Ekpyrotic model. He also co-developed the original inflationary cosmology framework in the early 1980s. He is not a skeptic from outside the field, and his position on eternal inflation is direct. His argument is that the inflationary framework has become so flexible, so capable of accommodating any observational outcome, that it has stopped functioning as science in any meaningful sense. A theory that can explain everything predicts nothing. If every possible measurement is consistent with eternal inflation, then no measurement can falsify it. And if no measurement can falsify it, you are no longer doing physics. You are doing something else. That critique matters, not because it settles the question, but because it is coming from one of the people who built the framework being criticized. Steinhardt is not attacking inflation from ignorance. He helped construct it. And what he is saying is that the field allowed a model to become so dominant, so deeply embedded in the standard story, that questioning it began to carry a professional cost that questioning other ideas does not. Think about what that means in practice. A researcher who builds a career on inflationary cosmology and the multiverse framework sits inside the dominant paradigm. Funding follows, collaborations follow, papers get published in high-visibility journals. A researcher who pushes hard on pre-Big Bang alternatives, who argues that the singularity boundary is real, that the standard model's treatment of the beginning is incomplete, that we need to take the bounce or the Brane collision or the cyclic geometry seriously as primary questions. That researcher is working at the edge of what major funding bodies consider core cosmology. The professional cost is asymmetric. Ask the hard question, and the institution does not follow. Stay inside the standard model, and nothing happens to your career. Does that sound familiar? Here is the part that deserves attention. The textbook version of the Big Bang, the one taught at every university, the one that gets cited in every public explanation of cosmic origins, treats the Big Bang as the absolute beginning. Time began. Space began. Before that, the concept of before does not apply. That is the standard framing. And it is technically defensible because general relativity breaks down at the singularity, so in some formal sense the question is unanswerable within that framework. But here is my position on that. Hiding an open question inside a framework's breakdown is not the same as answering the question. Saying our best theory cannot describe what came before is honest. Saying therefore nothing came before is not. Those are not the same statement, and the field has sometimes treated them as if they were. The researchers doing quantum cosmology know this. Their equations do not stop at the singularity. The bounce happens. The previous aeon exists mathematically. The inflating vacuum precedes the local event we call our Big Bang. These are not fringe positions. They are published results from serious people. The question is why the institution has not organized itself around them the way it organized itself around the search for gravitational waves or the imaging of black holes. When the most fundamental question in cosmology has been formally modeled by credentialed researchers in peer-reviewed journals, and the field's response is careful citation and no funded follow-up, that is not science being cautious. Here is what we actually know with certainty at the end of all of this. The Big Bang is a boundary, not a beginning, a boundary. The oldest light we can directly detect dates to 380,000 years after the event, and beyond that wall, our instruments go silent. But the physics does not. The equations keep going backward, and every serious framework we have for extending them, loop quantum gravity, conformal cyclic cosmology, eternal inflation, Brane collision models, arrives at the same basic result. Something was here before, not nothing, not an absence, something with properties, with physics, with a prior state that transitioned into the fireball we call our origin. Think about what that means for the geological record analogy. After a fire burns down a building, you find ash and chemical traces. The story behind the fire does not survive, but the chemistry does. The universe works the same way. Whatever existed before our Big Bang left a chemical aftermath, a gravitational aftermath, encoded in the curvature of space, in the spectrum of the cosmic microwave background, in the gravitational wave background that future observatories are now being built to detect. We cannot see the building, but the ash is there. The question is whether we can read it. Here is what is not settled. We do not know which model is correct. The Big Bounce, Penrose's aeons, the eternally inflating multiverse, colliding branes, these are not the same claim. They produce different predictions. Some of those predictions are testable with instruments we do not yet have but are actively building. The gravitational wave spectrum from before our Big Bang looks different under inflation than it does under the Ekpyrotic model. LISA and the Einstein Telescope will measure that spectrum. The CMB anomalies. Penrose identified either hold up under better data or they do not. The Planck satellite anomalies at the largest scales either have a standard explanation or they point to something older. These are not philosophical questions anymore. They are observational targets. And here is the part that does not get said enough. Every model in this video was produced by credentialed researchers, published in peer-reviewed journals, and built on legitimate mathematics. This is not the fringe. This is the frontier. The difference between those two things is that the frontier has testable predictions and the fringe does not. What came before the Big Bang has testable predictions. Several of them. What does that tell you about where this question actually sits? It tells you the textbook framing is wrong. The Big Bang as absolute beginning, as the moment before which there is nothing to say, is not the scientific consensus. It is the simplified version. The actual science is harder, messier, and points somewhere the simplified version does not go. We are not the first layer in the record. That is the honest reading of the published physics. The record goes deeper. How much deeper? What it contains? What fingerprint the previous state left in our oldest observable data? That is what the next generation of instruments is designed to answer. We have not answered the question yet. The record goes deeper than the Big Bang, and we are, for the first time in the history of any civilization on this planet, building the instruments capable of reading what is written there.